The other form of dome which Fuller was involved with is one which really doesn't have any natural antecedents, and this is a tensegrity structure. It's a structure in which the tubular elements, which are traditionally the elements under compression, and the string elements, the wire elements, which are traditionally the elements under tension, are strung out in this way in such a way that the tubes, the elements in compression, don't interact with each other at all. And they can be done, as you can see, in spheres, and they can be done in other configurations. Fuller somehow regarded this as linked in with nature, and although there are some hints, maybe some of the scientists can say, yes, that's a mechanism actually used in nature. In this case, I think that's not. And in fact, the tensegrity structures, maybe nature knows best, have been very difficult to apply in practical situations to existing buildings. There's a bridge in Brisbane, Australia, built by Cox Rayner Architects. The engineer is Ove Arup, and Cecil Valmond, who is featuring big in the next lecture, was then at that point the chief engineer in Ove Arup. And this bridge consists of a tensegrity structure, as you can see, the strings and the tubes, which are then used as a kind of sculpture to support the bridge. It's incredibly expensive. There's a lot of kind of overkill in a way. It's a wonderful, brilliant, almost a random seeming design, but it is in a way I think rather forced, because you're using that structure as in the same way that you could do it with more orthodox caving. It's expensive, visually exciting. If you're prepared to pay for it, okay. But the tensegrity structures probably have had limited practical applications, and it may be the economy of nature tells us, well, we can do this, but perhaps it isn't the most basic, simple and effective way to do it. The second of my examples of the dome structure is Andy Goldsworthy in the National Gallery in Washington, the slate sculpture called Roof, which I hope a good number of you will have seen. And what Andy Goldsworthy decided to do was to take a dome which was entirely corbelled without any adhesives at all, i.e. a series of flat beds. That's the indication of the basic structure on the top there. The hemispherical dome is a problem structurally. The shallow upper parts are okay, they're basically under compression, but the compression results in, as you can see, a lot of lateral stretching and a lot of tension in that part. That's for a pure hemispherical dome. The dome built from separate elements, I think the way that works, and I think Brunelleschi must have been using this in a way, his own way in the Florence Cathedral, is that each ring of stones, though separate, essentially make the ring below act as a solid ring, but it essentially solidifies that ring as a structural unit, which is why you can go up building those particular structures. This is the resulting sculpture in the National Gallery of Washington in slate, called Roof, with the man himself standing on them. They actually can stand the weight of a good number of people, as many people basically as you can get on them on the relatively small surfaces. The top left photograph is looking from the foyer of the IMP building, and the Andy Goldsworthy one is obviously inside. The one on the left I photographed from the outside of the building. It cuts through, as it were, the glass wall there. And there's another photograph from inside. Andy Goldsworthy works incredibly intuitively. When I was with him in Penpont discussing the roof, as we were doing a book for the National Gallery of Washington on it, he did his daily work. Each day he goes out in Penpont in Dumfriesshire in the Scottish borders and does a work, sort of keep himself honest. In this case it was a very cold day. Ice was on the river at the bottom of his property, and he collected up sheep's wool along the way and wove it off the fences where the sheep scratched off, and wove this wool into strands. which he then laid on a piece of ice in these concentric circles, launching the ice into the river where it underwent disintegration. He was mightily interested, as I was, to see that the wool insulated the bit of ice from it from melting as quickly, so the rings became kind of almost independent and began to move in relation to each other. So the plan and the unforecastable result was all part of the joy of this, an ephemeral work which he photographed. These are my photographs. He photographed it much better than I did, but it gives you an idea. I also talked to him about the origins of the idea for roof, and it was twofold. The first was slate, which is very much a Washington roofing material, and he did a series of works in a disused slate quarry in Virginia, a series of just spontaneous works which were done while he was researching slate as a local building material. And the other one was Jefferson's Dome. He said that he was very interested in the idea of a dome, much of which was submerged. And these Jefferson drawings, provided courtesy of a very efficient digitization service of the university, give an idea of the sort of submergence of that dome, the notion of dome, and the fact that the dome is quite is a relatively shallow section, that it isn't a hemispherical dome, and we know that that is actually a much more stable structure than producing the whole hemisphere with all the things that start happening in the lower regions of the dome itself. Goldsworthy's way of proceeding was entirely traditional, entirely intuitive. He's mightily interested and involved in what we would call primitive structures. This is a bridge in Yorkshire, which is, we don't quite know where it originates from, but it's the kind of structure which is artisanal, but at the same time, if you analyse it in engineering terms, incredibly sophisticated. And below is one of Andy's own slate arches, again using slate as the material, which has, they have uncanny strength, some of these structures. They're not ones that modern engineers have worked with, because obviously they've got no incentive to do so. He looks towards nature and towards traditional building structures, to the honeycomb, the hive structure on the left, and something which I know firsthand, the truly these very extraordinary cone beehive type structures in southern Italy, in Puglia, which again are corbelled. That's to say they haven't got these voussoirs, but they've got flat beds rather than the normal way of building an arch up in that sense. And it's a very hands-on job. He doesn't calculate initially, he doesn't do any structural work at all. He's not at all interested in why his things stand up. He imported his dry stone moorers from Scotland, who do much of the building work for him, and began to build the dome. This is the first dome underway. As you can see, it's a very hands-on, messy job at one point, and Andy Goldsworthy was off in hospital, having sliced his hand rather severely on these slates, which is a fiendish material to deal with. He was building the first dome, and it began to go wrong. The beds began to tilt in towards the centre, which is obviously, the corbelled beds didn't remain flat. They began to incline inwards. And he's aiming, as I say, at a hemispherical profile. And unusually, he began to draw much more than he normally does. And the drawings survive in the National Gallery of Washington, including his drawing board, which is the absolutely key point of reference on the left. And we can see him gradually widening the base of the corbelled structure, giving it a wider base and tapering towards the top. You can see that in both those images. The numbers, by the way, are not engineering calculations, they're dimensions. He never does engineering calculations.